Hello, general chemistry students. This is the second video in week 10 where we are exploring chemical kinetics and reaction rates. In this video, we're going to be learning about how do we determine these rates of reaction. So by the end of this video, you should be able to evaluate average rates of reactions, determine those instantaneous rates, and compare and contrast ways of measuring chemical kinetics. One thing you might have to review at the end of this video is converting stoichiometry reactions into rate comparisons. All right, so let's get started. So there is a relationship between reaction rates and stoichiometry. And so in this balance reaction, we have hydrogen gas plus iodine gas forms hydrogen iodide. And the stoichiometry of the reaction is 1 to 1 to 2. All right, so that stoichiometry of the reaction is going to affect the reaction rate of formation of hydrogen iodide and decomposition of hydrogen and iodine. All right, so for the above reaction, for every 1 mole of H2 used, 1 mole of H2 will also be used because it's 1 to 1. But then 2 moles of HI will be produced. Therefore, the rate of change is going to be different based on stoichiometry. All right? So to be consistent in the rate of change, we would multiply that stoichiometric coefficient, the rate, 1 over the coefficient times the rate. All right, so if we look at this and we want to compare the rates of all of these things, we have the rate of the change of H2 over some change in temperature. And notice my reactants are going to have a negative sign because reactants will go away while products will appear. And so here for my product, I have a plus sign, meaning that HI is forming. And so we're going to take 1 over that coefficient in order to compare those rates. So 1/2. All right, and so if we want to calculate the average rate of a reaction, this is really a linear approximation of a curve. So you would draw a line between 2 points and find out what is that slope of the line. And so we need to be careful when we take average rates because the larger the time interval, the more that average rate is going to deviate from what's called an instantaneous rate. An instantaneous rate is the rate at that particular point in time. So if you're taking a large sampling to find the average rate, it's not going to be very accurate. All right, so let's look at our hypothetical reaction. We're going from red to blue. So we start out with 100 molecules of red and 0 molecules of blue. And if we look at an average rate in 5-second intervals, so this is a smaller time period. In fact, that's actually our sampling. So we have a point every 5 seconds. And the longer we extend out that average rate, the more it deviates from the more it deviates from that instantaneous rate. All right, so let's analyze our reaction. So what we're going to do is we're going to look at our concentration of hydrogen and how that affects the concentration of the production of hydrogen iodide. We're going to look at the average rate of the disappearance of hydrogen and the average rate of appearance of HI. And notice the negative sign here, that means it's going away. And notice here that stoichiometric coefficient. Okay, so because we're forming 2, we have to take 1/2 times that rate. All right, so again, the stoichiometry of the reaction tells us that for every 1 mole of hydrogen, 2 moles of HI are made. All right, so we have a 1-liter container, and after 10 seconds, we're using up 0.181 of hydrogen. All right, so if you're wondering how I found that, so we start at 1, and if we subtract what we have left, that's how much we're using up. So we have 0.181 moles of H2. All right, and so therefore, the amount of HI that I form is 2 times that, or 0.362 moles of HI. All right, and going to 60 seconds, so I started at 10, now I want to look at 60 seconds. Here I've formed 0.699, or sorry, lost 0.699 moles of H2. So we used 0.699 moles of H2. So if you take 1 minus 0.301, that's how much you used up. So therefore, the amount of HI I form is 2 times that, or 1.398 moles. All right, so we can fill in the table for the concentration of HI that we form. So we can use the concentration of H2 to determine the concentration of HI that I must have. All right, and so now let's look at the average rates of this data. So the average rate is, of course, the change in concentration over a given time. So in the first 10 seconds, the rate of H2 is minus 0.181 molar. All right, and how did I get that? Well, I took 1 minus 0.819. All right, and that leaves us with minus 0.181 molar. Okay, so that's how much the concentration changed over that given amount of time. And the amount of time is 10 seconds, so we have to divide by the amount of time to give us 0.0181 molar per second. Okay, so now let's translate that, and so we can fill in the table for the average rate at each point for using up hydrogen. All right, and so we can also do the same for the average rate of the formation of HI. And so the number should be the same because we're taking half times the rate of formation. All right, and we can look at this graphically, where we look at the H2, so hydrogen going away, that's in blue, and the formation of HI, that's in yellow. And so by stoichiometry, we're not going to, if we start with 1 molar, we can actually get to 2 molar of HI just because we start with 1 molar of H2, and the stoichiometry is 1 to 2. Okay, so let's look at this graph and look at some rates or some average rates. So again, the average rate is a given time period is minus the slope of the line connecting hydrogen points. And so it's the negative slope because remember, hydrogen is going away, it is a reactant. Or we could look at the slope of the formation of HI, and so the average rate is going to be 1/2 times that slope. All right, so if we look at the first 10 seconds, and we can find the slope of those lines. And when we do that, the average rate for the first 10 seconds is 0.0181 molar per second. So either we took the negative slope of the disappearance of H2, or we took 1/2 the slope of the HI line. All right, so we can extend that further and go out to now 40 seconds. So here the average rate is 0.0150. Notice it's decreasing because now we've gone out to further amounts in time. And also notice how it deviates from the actual data. All right, it's deviating from the line because we've taken too many points. All right, we can go out even further. Let's find the average rate of 80 seconds. And when we do that, we get 0.0108 molar per second. Again, it's getting, over time, the rate is decreasing. And so then our average rate is going to feed into that. And also look, now we're deviating substantially from the data. And so really, when you want to look at average rates, it's always best to have a smaller time window, and also it's always best to use the first data points. And this is what later we'll talk about, the method of initial rates. All right, so those are average rates. So what's the difference here with instantaneous rates? So the difference here is that it's the slope at one point of the curve. So it's the instantaneous rate at a given time point. Okay, and so this can either be determined by taking the tangent of the curve, or you take the first derivative of the function. Okay, so the first derivative at that point. What I'm going to show you today is how do we do the tangent. Okay, so here we have, we can look at the instantaneous rate at 50 seconds. Okay, so we can draw a triangle, and the tangent of that line that crosses 50 seconds is what we need to determine. And when we do that, we do that with either the concentration of hydrogen or the concentration of HI. Of course, always incorporating that idea of stoichiometry. So if we look at hydrogen, the instantaneous rate at 50 seconds, we draw that triangle that gives us a concentration change of 0.28, and then our other side of the triangle, we're going to go 40 seconds. Okay, so we are going 20 seconds prior to that 50-second mark and 20 seconds after that 50-second mark, so that the 50-second mark is right on that curve, the data curve. Okay, all right, so the rate here is 0.007 molar per second. If we use HI, we're going to do the same way, except remember, we're going to take that rate times 1/2, because by stoichiometry, for every 1 we use up of H2, we gain 2 of HI. And so here we have 0.56 divided by that 40 seconds times 1/2 gives us the same rate. So at 50 seconds, regardless if you use the reactant, so the disappearance of that reactant or the formation of product, you should get the same instantaneous rate at that given point. All right, so let's work on a problem. So we have this reaction where we take hydrogen peroxide with iodide to form triiodide, and this is a reaction that's colored, and so we can monitor the formation of triiodide by the formation of the color that forms. So we have 1 molar iodide that changes to 0.868 molar in the first 10 seconds. Okay, so we know we can calculate the the rate of change of the iodide. And then we're going to use that information to calculate the average rate of H+. Okay? So remember, we have to incorporate the stoichiometric coefficient. So the rate is equal to minus 1/3 delta I delta T. Okay, so the delta I is 0.868 minus 1, final minus initial, and divided by 10 seconds. Okay, so we get a rate here of 4.4 times 10 to the minus 3. Right, so now what we want to do is take the rate of the change of iodide and compare that to the change of H+ that we would need. So we can take the rate. Remember, here we have negative 1/2 delta concentration of H+ over the delta T. Okay, so again, 1/2 because of stoichiometry. So that means that if we want to solve for the concentration of H+ per time, we would take minus 2 times the rate. Okay, so we solve for the rate, so we can just really take minus 2 times the rate, and we get negative 8.8 times 10 to the minus 3 molar per second. All right, so really we're just using stoichiometry here to determine the rate of H plus decomposition. All right, so let's work on another problem here. So if we have 240 grams of NOBr, given the chemical equation, it's going to decompose in a flask to produce NO and bromine. And we're going to look at this reaction in 5 minutes. Let's find the average rate of bromine in molar per second. Okay, so let's take this apart a little bit. So what do we have? We know we have 240 grams of NOBr, so that's our reactant. We know we have a 200 ml volume and that the time is 5 minutes. All right, so let's think about what we need to find. Well, we need to find the rate of change of bromine in molar per second. Okay. What are our relationships? Well, we know we have 2 moles of NOBr for every 1 mole of bromine. Right? We know our molar mass, and we know that 1 mil is 0.001 liters. Okay, because remember, molar is moles per liter. All right, so how are we going to do this? Well, first we need to convert NOBr into moles of NOBr. Right, so we're going to use the molar mass. And once we've done that, then we're going to use the balanced equation to determine how many moles of bromine do we have. Once we have moles of bromine, we can turn that into molarity. And then we can turn our minutes, which is 5 minutes, into seconds. That's going to give us a rate. Okay, so now we're prepared. So let's take our NOBr and turn that into moles of bromine. So we're going to divide by our molar mass, divide by that stoichiometric coefficient, and we get 1.09 moles of bromine. All right, now we can find the molarity of bromine. All right, so we're going to take our moles divided by our liters, and we get our molarity of bromine. But we're not done yet, because now we still have to determine how many seconds are in 5 minutes. So we take our 5 minutes times 60, and we get 300 seconds. All right, so now we have everything we need to get to the rate of bromine production in molar per second. All right, so we're going to take our 5.45 divided by 300, and we get a rate of 0.018 molar per second. All right, and so lastly, we're going to talk a little bit about how do we measure these reaction rates. So I keep giving you concentration, but there must be some way that we can measure those concentrations. And actually there are lots of ways to measure concentrations, but I'll just talk about a few of them. And really there's 2 ways you can measure reaction rates. All right, and they all have to do with the time of the reaction. So if the reaction is complete in less than 1 hour, you might use something that involves continuous monitoring of the concentration. And we'll talk about one type, which is called spectrophotometry. Or if a reaction takes a very long time, you might consider sampling, right? So we'll talk about an example of how you might sample a reaction. All right, so for continuous monitoring, I want to focus here on spectrophotometry. There's lots of different ways to measure concentrations. Probably the most popular way is to measure by spectrophotometry, and that's going to measure the amount of light at a particular wavelength that's absorbed by the sample. All right, and really importantly, if we remember our color wheel, so this is going back to first semester when we talked about light. The component that absorbs, it's going to absorb its complementary color. All right, and so what you see is not what's being absorbed, it's the complementary color that's being absorbed. All right, and if we want to do sampling for a reaction that takes a really long time, like maybe days, what we would do is we would take aliquots. And when you take aliquots, you can do a couple things. You can titrate to analyze the components of your reaction. You could do what's called a gravimetric analysis, which sometimes has to do with titration or a combustion reaction. But one thing that I'm going to talk a little bit about is this idea of gas chromatography. So if we're taking aliquots of a reaction, we can analyze the components of a mixture using gas chromatography if the sample is volatile, because it has to get into the gas phase. And then you separate that mixture in terms of its chemical components. All right, so let's talk about spectrophotometry for just a second here. So in spectrophotometry, you have a light source. Imagine a light bulb where the light is all wavelengths of light. That light is going to go through a slit where it is then diffracted by a monochromator. And that monochromator breaks up that light into its individual wavelengths. And it's that individual wavelengths that's going to go through the sample. And here the sample is going to either absorb light or let light pass through, depending on its chemical composition or electronic structure. And then we can detect the amount of light that's absorbed. What we see on the computer is we see a certain wavelength of light, and over time, so this is absorbance. So absorbance at some wavelength of light versus time. So that's what we're looking at on the computer, because remember, we're analyzing reaction rates. So over time, our absorbance is going to go down. That's indicating that, in this case, our reactant is going away. Okay, so absorbance is proportional to concentration, in this case of our reactant. All right, so here's an example of gas chromatography. So this would be if we take aliquots of our mixture. So we would take our aliquot of our mixture. So imagine you have a reaction going in the hood. You're going to take a little bit of that and you're going to put it into the gas chromatography. And so in gas chromatography, you're using gas to move chemicals across a column. And based on its chemical composition, those components of the mixture are going to come out at different time points according to their chemical composition, and that will be denoted on the chromatogram. Okay, so imagine this is your sample of interest. Okay, and so what that would say to you is, yeah, I have my product in there, but maybe I need to let the reaction go a little bit longer so that more of my reactants go away and more of my products grow in. All right, so that's it for video 2 in determining reaction rates. Thank you.